with first introduction into physics-informed neural networks, and then we will dive into detail about magnetic field simulations. So for the majority of talks during this conference here, we were dealing with the regime of big data. So this is what we have here in this graph here on the right-hand side, which means we have a lot amount of data, for example, in terms of like input and output pairs, but we have very little understanding of the underlying physics. So a good example for this would be, for example, the classification of images. So it's very hard for us to describe physically how the mapping works between a certain image and the classification label, but we can create large amounts of data, and then we can perform our supervised training to learn this mapping. So for today's presentation, we'll mostly focus on the regime here on the left-hand side, where we have basically very little amount of data available, where we actually want to discover new data, but we have understanding of the underlying physics. And this enables us basically to learn something new about our data. So this is where we are, what we will talk about today. So in the center, we have also this regime where we have some data and some physics, and this would enable us further to learn something new about our underlying physics. But for today, we will focus on this part here on the left-hand side. So, and specifically for this regime where we have only a very limited amount of data available and a concept of the underlying physics, there's this tool which is called physics-informed neural networks. Here, the primary task is not to perform some sort of general mapping function or to learn a general task, but it's for solving numerical simulations in the sense of performing a mesh-free simulation of partial differential equations. And this works in a way that we have basically like two concepts here, where we'll focus today on this part here, which is data-driven solution. So we're using our partial differential equations to find the solution and discover new data with this. And specifically, we're dealing with this regime where we have basically only boundary conditions available, and we want to discover through the physical equations the underlying data. And the primary advantage that we have from this approach is that physics-informed neural networks are really good at integrating noisy data with maybe incomplete physics. So it's very flexible in that regard. It's also very computational efficient. And especially when we are dealing with domains that are highly dimensional, this mesh-free simulation that we are using, so it's not based on a grid, becomes really important. But more about this on the next slides. So to better understand what we're aiming for, we can have a look at this at this example here on the right-hand side. So what we are dealing here with is an example from fluid dynamics. So we have information about the data in this box. So this is our boundary condition, basically. And then we use the Navier-Stokes equations to find the data in the remaining part of the box. And we can see that with this, we can basically drive the simulation through those equations and get the solution in this entire domain. So since we're here at this machine learning conference, everyone has a concept of how to deal with supervised applications. So you're all familiar with training set, test set, validation set. This does not apply here. That's very different from this approach. Here we are dealing with a way of discovering new data. We are not trying to approximate something that is already solved, but we are building for something new. And here's basically the overview that tells you how this concept works. So on the left-hand side, this is what we are used to. For most supervised applications, we have our inputs. We feed them into a neural network. We get our predictions. Then we can compare them to our target, compute our cost function, the loss, and then perform an optimization of our weights in order to match those two. For physics-informed neural networks, this is very different. So here we want to learn something about a single problem, and we're only solving a single simulation volume, basically. And here we're using the concept of a neural representation. So in this case, the neural network itself is basically the volume that we're trying to solve, where we use the input coordinates that map to the individual values in our simulation. So in that sense, it's a neural representation of this volume. So what we are doing is basically we are feeding in input values in terms of the coordinates. So in this case, for example, like 2, like a spatial dimension, and the temporal dimension, so x and t. and then we get our function f from x and t at the respective points, and then we can perform basically two steps for the updating, where we first have a boundary condition, for example, so we can say the point 0, 0 equals to 10, and we can optimize this neural network to match this value at this boundary condition, so that's very straightforward. But on the other hand, we can also use a physical model and use basically physical equations for every other point in the simulations. We can just put random points through our neural network and then enforce physical equations. And what you can see down here is a partial differential equation. And here the primary advantage that we have from physics-informed neural networks is that this here is a differentiable function, meaning that whatever we get here as an output is fully differentiable with respect to the input coordinates, and we can make use of this concept of automatic differentiation, meaning that we can compute smooth derivatives from the function f from this neural representation with respect to the input coordinates, from which we then construct our physical equation that we can optimize for. So this is the basic concept of physics-informed neural networks, and now I want to move to the more specific application, and I hope after that it's clearer what this is all about and how this application actually works for then numerical simulations of the solar magnetic field. But as a quick first introduction to this, why are we interested in the solar magnetic field? Why are we interested in simulations? So the primary point here is that the majority of our observations that we have available come from, in terms of magnetic field observations, come only from a certain layer, from the photosphere, where we have the best observations, where we observe the most amount of detail. But on the other hand, if we want to fully understand solar eruptions, the energy buildup and the energy release process, a full understanding of the 3D topology is necessary. And also in the other aspects of predicting flares, on better understanding flares, we need really this full understanding of our system. So for this reason, there are common approaches that are applied for this. A valid approach, for example, for obtaining the magnetic field or estimating the magnetic field in the upper atmospheric layers, so in the solar, specifically in the solar corona, is our nonlinear force-free extrapolation methods. So here we use the photospheric vector magnetograms that we observe as boundary condition, and then we use two partial differential equations, coupled equations, in terms of the divergence-free equation and the force-free equation to estimate the magnetic field in the entire simulation volume. So we are solving those two equations, and from this we obtain the magnetic field in the upper layers. On the other hand, we have also more advanced techniques that also consider time evolution, where we have usually numerical integration schemes in terms of MHD simulation, for example. But those can be very complex and computationally demanding. So specifically for both of these methods, or for simulation methods in general, we are usually very restricted in the way that we are dealing with the input data that we have. So usually we need a lot of pre-processing in order to work with this data, and most methods are very computationally expensive. So here we want to approach this with the use of physics-informed neural networks. So the first part here is how to solve nonlinear force-free extrapolations with physics-informed neural networks. So this is the first part of this application series here. And this is the concept that we are using. So this is in line with what I have shown you previously, but now for the specific application of to magnetic field extrapolations. So this is an iterative process that we are following, and the task that we are trying to accomplish, you can see it here on the left-hand side. We have our simulation box. We have the observation at the photospheric level. This is basically at the bottom of our simulation, the bottom boundary condition. And the task is to find the magnetic field in the remaining box. So remember, we are not solving a general task here, but we're solving just a single problem. So we only have one observation, and we want to find the corresponding magnetic field in this simulation volume. So we apply this for each individual case separately. So we start by sampling points first. So for example, for the boundary conditions, we can just take from the spatial grid x, y, and 0, and feed them into our neural network, which takes as an input the coordinates, x, y, and z, and gives us as an output the magnetic field vector at the respective points. So for the boundary condition, this is quite simple to match, because at each of those points that we actually have the observations from, we can just feed them here through, match them to the observations, and optimize our neural network to match those values. On the other hand, we want to find the magnetic field in the remaining volume. So for this, we pick random points in our simulation volume in terms of x, y, and z, feed them into our neural network, get the respective magnetic field vectors at the individual points, and then we can use this concept of automatic differentiation to compute from this output here the derivative with respect to the input coordinates. Having these derivatives available, we can then construct our physical model in terms of the divergence-free and the force-free equation, so those two partial differential equations, and then we can optimize the neural network to satisfy this condition in the simulation volume. So this is an iterative process where we are optimizing for the residuals of this equation and also for the deviations from the boundary condition. So we basically sampling points all the time over multiple steps and optimize our neural network for those two conditions. And in the end, we find the solution that satisfies the boundary condition at the bottom and the physical equations in the entire simulation volume. So of course there will be some deviation, and this is also where the strength of this method is, that we can smoothly converge to a solution, where we still have a certain trade-off between the two conditions if they don't match. So as a first step, we wanted to verify that this method is actually applicable for the problem and that this works. So for this, we use a semi-analytical solution where we have actually a ground truth that we can compare to. So we want to solve this single problem. So what we're doing is we construct the solution of this magnetic field. This is commonly used as a test case for coronal magnetic fields. And then we use the bottom boundary condition as input to our model, and then we compare the results that we obtain to the analytical solution. So specifically, we used the configuration from Schreiber et al., where they compared 6 individual methods. And what we found is that we achieve almost identical solutions to the analytical magnetic field. And you can see this down here. We have the C1 case, basically, where the primary difference is that we have all boundary conditions available. And the metrics here are correlations between the vectors and deviations between the vectors, and epsilon here gives the ratio of the energies that we obtain. So we see that we get identical energies, and the matrix range have a maximum at 1. And we can see that we achieve, for this configuration, basically a perfect solution. And this also outperforms all the methods that were used in this comparison study here. For the C2 case, we can see that we have slightly lower values here, performance values, which is due to the fact that for this configuration, we only use the bottom boundary as an input and approximate the remaining boundaries with a potential field, which is a common approach for this. And also what we have to do when we move to applications for the solar magnetic field, because there we don't have the side boundaries and the top boundary, but have to approximate it. So we have some deviation because of that. But if we have the full boundary conditions specified in a correct way, we can see that this gives us basically perfect solutions. So with this, we can move forward to observations. And here we apply our method to HMI vector magnetograms. And the first thing that we have to appreciate here is that the physical model that we're using is not correct. So the force-free assumption does not hold at photospheric heights, so we'll have some deviations there. And the way that this is usually approached by force-free extrapolation methods is to pre-process the field in a way that is suitable for the input. For pins, we are quite flexible in that regard, and we can find a trade-off between the boundary condition and our physical model. And here we define this as a certain weighting parameter, which we call lambda, which basically emphasizes either the boundary condition or the physical model. And the effect that this has, you can see here on the right-hand side. So when we start with a small lambda, we are basically neglecting the physical condition, emphasizing the boundary condition, and we get a very, so that the field that we get in the end is very close to the actual boundary condition. But when we increase the importance of the physical model, we can see that the magnetic field becomes smoothed out to become more force-free, that we have a better solution of our force-free assumption. And you can also see when we plot this here, with the two metrics. So on the x-axis here, we have the difference to the observed photospheric field. And on the y-axis, So this is the boundary condition basically, and on the y-axis we have the deviation from our physical model. So the ideal point would be down here at 0, 0, but this is not attainable. When we vary our lambda parameter, we can basically discover the solutions that we have, and we can see that both of those metrics are at odds with each other, so there is no perfect solution, but there's a certain trade-off line where we can explore solutions. And when you look at those two black symbols here, those relate to recent state-of-the-art method, to a recent state-of-the-art method for phosphor extrapolations, and from this we can see that this same trade-off line, basically this limit, also holds for other methods. So as a next step, so to better understand if this is a valid approximation, we move forward to comparing our results to actual observations. And the way to do this is by comparing our extrapolations to EOV observations. So we basically perform our method on this active region, and then we plot magnetic field line traces, highlighting the primary components of the active region. And you can see that we obtain the central flux rope here, also identify the secondary flux ropes, and this is in agreement with the EOV observations. And we were also able to identify this eruptive structure up here, which becomes visible briefly before this flare event happens. But the usual way and the most beneficial way of using this approach is for the understanding of energy buildup and energy release processes. So we are primarily interested in a series of extrapolations and in the temporal evolution of those events. So conventional methods approach this by performing extrapolations for frame by frame, basically. And usually those methods require about 6 hours per extrapolation, and from this you can see that this becomes quickly computationally very expensive. So it's not applicable in real time. So here we make use of a different approach, where we assume that adjacent solutions are very similar. So what we are doing is we start, for the first frame, we take the first magnetogram of the series as input, train our model on this, which takes about an hour, and then we only exchange the boundary condition and converge to the next solution by continuing the training. So we basically extract snapshots of our simulation at each point in the series, and from this we can construct our entire series. And this is very fast and computationally efficient, allowing us to get a new extrapolation within 2 minutes. And we performed this for this active region here, 11158, where we use 5 days at full cadence, so 12-minute cadence, in order to get this full extrapolation series. And the total computing time is less than 13 hours. So which basically allows us to perform magnetic field extrapolations in real time. And what we get from this is shown here. So the top, so this is a video of the simulation that we have. So on the top you can see the observations. So we have the magnetic field at the center. We have EOV on the left and UV on the right. And at the bottom you can see the magnetic topology in terms of the integrated current density. And at the center you can see the free magnetic energy. You can see this buildup while the active region evolves. And on the right-hand side, you can see the running difference of the free magnetic energy, which relates to the flare events. So in order to have a closer look at this, we can examine the integrated quantities of this. So from the series that we have constructed, we can then compute the magnetic energy, so total magnetic energy, the free magnetic energy, the magnetic helicity, and as a reference, you can see down here the flare history in terms of the ghost flux. So the dashed lines here indicate the flare events, and what you can immediately see is when we have this X-class flare in our series, we observe a sharp jump in the series in terms of helicity and free magnetic energy, which directly relates to this to the flare events. What you can also see here is that we have still an energy buildup in this phase here, without a certain drop, but observe an M-class flare at the time. So when we have a closer look at this, we can see that this, in terms of the depleted free magnetic energy, which you can see in this plot here, we can see that this relates to this polarity inversion line on the left-hand side. So while the active region is still evolving at the center and energy is being built up, which you can see basically in this integrated quantity, we can see that we have an energy release to at one of the secondary polarity inversion lines, which is in good agreement with the EUV observation that we obtain of this flare event. So this looks all very realistic. And when we compare this to the actual X-class flare, which happens then later, we can see that this one directly relates to the central polarity inversion line, where we have this huge amount of energy release in this series. So all of this was now applied to this single active region. So you might ask, is this applicable to other active regions? Can we use the same method for other scenarios? And the answer is yes. So we applied this for 66 individual active regions, which were all related to X and M-class flares. And what we obtained from this is this metric here, basically. So on the X-axis, you can see again the deviation from the boundary condition, and on the Y-axis, you can see the deviations from the physical model. And we have a certain scatter in an area. We have basically a certain scatter here, but we obtain basically independent of the size of the active regions that we're considering high-quality solutions. And the result that we're obtaining is primarily driven by the lambda parameter that we are choosing, so the way that we set up the simulation, basically, and it's not driven by the magnetic, not primarily driven by the magnetic configuration, meaning it's very robust in that sense. And this is also freely available online. So if you want to use this, actually, you can just go to this Google Colab link. There's also one on the last slide, where you can basically put your own active region number and perform an extrapolation from scratch using online resources without setting up anything on your environment. And with this, I want to move on to the next topic. So this basically concludes the first results that we're working on. So the next aspect is, how can we improve this? And how can we make actual use of this concept of physics-informed neural networks to move this whole this field forward, actually? And thinking about the future, we will have multi-height observations of the solar magnetic field available. And the question is, how can we incorporate this into our simulations? And here we also have to face first the problem, because what we're observing is not assigned to a specific surface. So when we have a magnetogram, it's not a flat layer as represented here. This is only what we're observing, but it's actually, the line formation happens at different heights. So we need to account for this first. And the way that we do this here with this approach is that we include this into our model and give our model the flexibility to basically adjust the height of our observations first. So it's within the same framework, basically, but we add a second network at the first level, which we call a mapping model. So on the left-hand side, you can see basically two observations. We have one from the photospheric level, and then we have one from a chromospheric level. We can then input the individual coordinate points that we are having, so in terms of X, Y, and Z, and then allow the model to modify the Z coordinate. So we get an X, Y, and Z prime as an output. And from this, the model can then basically adjust the height surfaces in a way that fit with the overall model, and this then works all end-to-end with the model that we are training for the force-free extrapolations, which you can see, which is basically the concept that I was introducing earlier here on the right-hand side. So this is then optimized again for the physical model and the boundary condition in the very same way. So in order to understand how this works before going into applications, we wanted to check this. And the way that we did this was with simulations of Muram. So there we have basically a field which is not force-free. So we will expect a certain deviation, but we want to see if by introducing additional layers of the magnetic field into our simulation, if we can achieve a better result that is closer to the actual field that we are simulating here. So here we have actually a ground truth that we can compare to, and we extract those 5 slices here, which you can see. So those are the magnetograms on the left-hand side, and on the right-hand side, you can see the corresponding height as the heights where the individual points are obtained from. So ranging from photospheric levels to chromospheric levels. So I said this is like a realistic approximation that then should also work for actual observations, because this is a field that doesn't even satisfy the force-free constraint that we're working with. And when we use this, we first examine what's the actual improvement. which is given down here. So when we have a look at the Murum simulation first, what we can do is we can compute this factor of force freeness. So this is given here on the right-hand side. This is basically giving us the angle between the magnetic field and the currents. So we can see that this is definitely not force-free. Our model will always try to satisfy the force-free assumption. And what you can see from the metrics is, so we have here 3 individual cases, where the first one is about extrapolations. So we are just taking the photospheric slice and perform the extrapolation as in the usual case with the same metrics. So the maximum is at 1, and here we want to have an ideal value of 1, and we can see that we have a strong deviation from the actual field. When we then introduce the slices without any mapping, we get a rapid improvement actually of the metrics. But when we have this flexible height mapping here, we get the best results. So when we allow the model to also account for certain height levels of the formation, of the line formation, then we get the best results out of this. And when we look at this in terms of height, so here you can see basically the vector correlations on the left-hand side, and on the right-hand side you can see the energy ratio. We can see that we get throughout better results by applying this mapping between, by applying this mapping of the individual surfaces that we're observing. So this means that we can incorporate this new data into our extrapolation method. But this also gives us the opportunity to actually examine then the height surfaces that we are obtaining. So the height surfaces are never used as an input to the model. But in the end, when the model is finally trained, we can then sample the individual points and reobtain the height surfaces that we are observing. And what you can see here on the right-hand side is the comparison of our PIN model, what this gives us as height estimate of the individual magnetograms. And on the right-hand side, basically here, you can see the comparison of the ground truth. And we can see especially for the larger heights, so when we move more to chromospheric or coronal layers, we can see that we are very close to the actual observation. So this gives us a way to examine where the observations is obtained from. So this ends the topic here, and the next step that we are currently working on is applying this to actual observations, which then will give us also an estimate about the height where we are actually observing. And with this, I want to come to the last topic, just really briefly, which is about advancing this forwards to MHD simulations. And specifically, we want to do this through the magnetic induction equation. So the idea here is, let's make use of this PIN concept. Let's make use of this enhanced flexibility that we have in terms of the input data to advance the complexity of the equations that we're using, but also introduce additional observational constraints in our simulation to achieve more realistic observations. So here we also consider the time as an input, and then we perform a mapping from the spatial coordinates plus the time through our neural network, and what we obtain is the magnetic field vector and the velocity field. And the idea here is to solve the magnetic induction equation, where we have this time dependence of the magnetic field. We have the velocity field included, and on the right-hand side, thank you, perfect. And on the right-hand side, you can see we have also this diffusion term. So here we are only solving the ideal magnetic induction equation, so this one cancels out. But since our model is optimized iteratively, we have a certain deviation. So where this induction equation cannot be satisfied, we will have a certain deviation, which we can then potentially link to magnetic diffusion. As a first step, we want again to verify that this approach is even valid. And we applied it to an analytical solution of a spheromag, which is an expanding spheromag solution that is both inductive and force-free. So we should be able to obtain basically a perfect solution for this. And we mimic kind of the solar case where we have only observations of Dopplergrams, so meaning only the line of sight component or the C component of the velocity field is available. And we find the X and Y component, so basically the horizontal flows of the magnetic, of the velocity field through the induction equation. So here you can see a short video. On the left-hand side, there's the analytical solution, and on the right-hand side is the result that we get from our physics-informed neural network. So this looks all very similar, and especially when we look at the metrics, so again, the maximum here is at 1, we can see that we obtain very good solutions, both for the magnetic field vector and the velocity field vector, when we compare to the analytical solution. And what's also very interesting here is we didn't use the X and Y component as a boundary condition, but the X and Y components that are then the result of the network after the training, basically, have only a deviation of 5% from the original values. So this also allows us to estimate, ideally, velocity horizontal flows from this data of vector magnetograms and the line of sight component of the velocity field. And as a last slide here, I want to give you a short outlook on how this could further evolve with the application to a flare event with an actual observation. So here you can see the reference for EUV. So you can see the evolution of this active region here. This is the simulated magnetic field at the photospheric level. You can see the velocity field. Basically the red arrows here indicate the horizontal flows that we're observing, and the magnetic topology is given here as integrated current density. So you can see this buildup of currents and close to this polarity inversion line. And the most important thing here, and maybe the most interesting thing here, is what is labeled here as diffusion, which is the residual of the induction equation. So this corresponds to this part. So we are not optimizing for this, but when we have deviations from the induction equation, basically is where we expect that the ideal induction equation breaks and that we have magnetic diffusion. So when we compare this to the observations in EUV, we can see when this flare event happens here on the left-hand side. Let's restart the video. So if you look at this, and then you can see this sudden brightness increase, and then correspondingly, we also get here a large residual term from our induction equation. So as a summary of this, we applied physics-informed neural networks for magnetic field simulations. We achieved state-of-the-art results for nonlinear force Fourier extrapolations, which basically enable us to obtain consistent solutions without any data preprocessing, which is usually required for other methods, but here it's model intrinsic. And it's also the first method that can achieve real-time magnetic field extrapolations, which has great potential for the next generation of space weather monitoring and flare prediction systems. But the real advantage that we get from physics-informed neural networks in the context of simulation methods, specifically magnetic field simulations, is the way that we can introduce new observations and move this forward, basically, adding more complex equations and finding more flexible solutions in even less computing time. And specifically, introducing multi-height measurements can have a great benefit for the future of extrapolation methods. And we can use additional observing constraints like Dopplerograms or even EUV images to further to get more realistic observations out of this at the end. And the overall goal that we are following is to solve this, to go forward and go to for full MHD simulations. So as a final note, the project all the codes are publicly available. You can also find the Google Colab notebook, which allows you to play with this by yourself and to perform these extrapolations basically online. The paper got recently accepted for Nature Astronomy, and the remaining studies are still upcoming and in progress. Thank you for listening, and I'm looking forward to your questions.
Well, wow, that was amazing.
Thank you.
So many questions, though, but I'll try to consolidate them as best as I can. So for the nonlinear force-free solution, you showed some divergence of the divergence-free condition, let's say, in units of Gauss per pixel. Mm. What would be perhaps more meaningful is to find the percentage difference, because, you know, the magnetic field changes for different heights, it becomes much weaker. So right. This would give us a much better idea. Have you done that?
I haven't done this comparison, but on the other hand, definitely divergence freeness is like the primary physical constraint, right?
Right.
So this is what we actually want to set to an absolute value of 0. So for this study here, we use the divergence-free constraint in the very same way as other methods, but what's the actual plan? Let me go back. Right. So we have this here in our condition. This is also the way that recent extrapolation methods work. But a much better solution is to that we don't construct here the magnetic field in terms of B, but we can construct here the vector potential. And from the vector potential, we can immediately compute the magnetic field, which would give us automatically a solution that is completely divergence-free. And the code is actually up and running, so it is like even included in the extrapolations. So if you're interested in having a stronger deviation from the force-free equation here and having this physical constraint perfectly satisfied, it just means this additional mapping through the vector potential, which is also what we are using for the later stages. So when we are dealing with the MHD simulations, the divergence freeness is already included through the vector potential in the solution.
Yeah, you can do that, provided that you can solve partial differential equations at acceptable accuracy. So at accuracy that is comparable to the analytical methods, which are much lower, but they achieve, an accuracy which is closer to machine accuracy in essence. But that's a long story. Then the force-free equation. Again, another measure for doing this, for seeing how well you are satisfying this equation, is to find the average angle between the current density, the electric current density, and the magnetic field. Have you done that?
Yeah, those are. This is also the metric here.
Is it the angle?
That's the current weighted angle. We have the full comparison of all the quantities basically in the paper.
Okay.
But this is the angle that we obtain. This is like multiplied by 100 here, right? But it's the current weighted angle between the magnetic field and the currents.
Good. And then you mentioned the active region 1158, in which you tried full 5 days at full cadence, and the total computation took less than 13 hours.
Yeah.
What was the spatial resolution of these things?
Usually, we did the binning by 2, so we reduced the resolution by a factor of 2.
By a factor of 2, okay.
Right, but actually it doesn't matter for this method. So when we go back to this one here, so all of the way that this works is by just sampling points. And in the end, we don't have a mesh. So for the entire simulation, everything is incorporated in terms of this X, Y, and Z coordinates. So we have no underlying mesh, basically. It's just a different way of sampling the data points, and having a higher resolution is not strictly beneficial here. So we can go lower in resolution, but it also doesn't change our computing time. It's only the result could change if we use a higher resolution. But it's just the amount of data points that we are sampling. Basically, the primary constraint is given through the disagreement basically between the boundary condition and the physical model. It's not the resolution that is limited here in this case. So it's like, in the end, of course, like when this all is like trained, so it's like all of this is mesh free, in the end we always go back to the original magnetic field, right? So by just taking points in the simulation volume, point by point, sample each of those points and then construct our solution from this, which we then can compare to something that is mesh based. Right, so this of course then takes more time because then we have to sample 8 times more.
When you're pre-processing, you're smoothing BZ as well at the photosphere?
Right, this is like what we obtain basically model intrinsic. This is what you can see here in this plot. So basically when we are like enforcing the boundary condition here, we get something that is very close to the actual magnetic field. But then when we move forward to having, if we are aiming for a solution that is in very good agreement with our physical equation with the force-free assumption, then we can see that we have to smooth out that the model basically smoothes out this boundary condition.
Sure. Try not to smooth that much BZ, but BX and BY, because you can always get a force-free condition at the photosphere without BZ. With that, you're changing the magnetograph.
That's a good point as well. That's like also what is included. So here I just put this equation, but this also includes the error estimates that we have that are larger for BX and BY. So the model has a certain range where it can deviate from the boundary condition in terms of the errors that we estimate from the HMI magnetograms. And there we have a larger error for X and Y, so we automatically get a stronger deviation in for those two components. Thank you.
Thank you. Do we have, okay, excuse me, we have one question. Awesome. Great talk. I was just wondering, have you even thought about using Fourier neural operators? I know that they've gained a lot of traction in not space weather, but normal weather forecasting situations, and you're solving partial differential equations there. Would that be beneficial, do you think?
To use what? Sorry?
Fourier neural operators. So it's basically solving it in Fourier space rather than in physical space.
Oh, yeah. So it's kind of like, right. I mean, like, so the first part, I guess, like the proper answer is for this. This is like related to positional encoding, where you first perform a mapping of the x, y, and z coordinates into Fourier space through sine and cosine functions, basically. And yeah, I tried that. It's also like included in the software, but it's not beneficial. So it turned out that when you compute the derivatives, apparently, so basically it's much easier to fit the boundary condition then, because what this does is kind of having, giving the model basically the ability to better learn high frequency features, and then it more easily matches the boundary condition. But here we have such a high volume, we have basically no constraint from the boundary condition, and it looks like it's quite difficult for the model to actually extrapolate then in this Fourier space. And we usually obtain much smoother solutions and faster solutions that are in better agreement with the physical model when we don't do this mapping first. On the other hand, what's included in the model is, so the way that this is set up is we have sine activation functions, which is actually kind of beneficial. So we want to use sine activation functions in the model, but we don't want to do this positional encoding first. I guess that's the second answer to this, yeah.
Very nice talk. I'm wondering, I have two questions. This method can be applied at every height, right? Not just on the photospheric layer, also like way later.
Yeah.
So it would be really interesting to compare like also with radio observation and stuff like that. And I was wondering about that. Did you consider to also apply some equation for the emission so that you could directly compare it with the observation before you compute the magnetogram? Like
I would even go one step further and would say, why not just include the radio observations in the simulation? So when we're doing the multi-height observations here, I mean, like obviously it would be a nice aspect to compare it. I would say like definitely what we obtain at the highest levels is also what you can see here. This is the energy ratio on the right-hand side. So we can see that basically all the methods kind of deviate when we move to the greater heights. So it's like very unconstrained there. We are pretty far away from our boundary condition. So it's really difficult to get a proper estimate there. So we'll always have some larger deviations when we have some magnetic field observations from the very top. So I was considering adding like this height surface, like another height surface basically at the top as a constraint, which could be, for example, something like from a potential field. But yeah, using radio observations, on the other hand, could be even more beneficial because this is the actual observation that we have at a very large height, and we can even include it in this flexible height mapping that we can basically constrain the magnetic field solution at the top of our simulation volume. So yeah, that's actually a great idea.
And another question, like, right now you have the magnetogram, so that's your ground truth, right? But could you actually include like an emission model so that you can constrain directly from the intensity of the
That's a perfect question, yeah. And I have a backup slide for this. That's like what is planned for this approach. This is when we are going further. And you saw the presentation about sun nerves on, I think it was on Wednesday. So this is what you saw about the 3D reconstructions of the sun. And the future goal that we're aiming for is when we move towards MHD simulations is that we have a lot of additional parameters that are like unconstrained. So how can we further constrain them? And one possible solution is through the EOV observations that we have at hand. And this method can actually provide us with the ability to actually incorporate this into our simulations. So what we can have here then, so this is like this mapping model again, X, Y, C, and T. And then we also take basically points from our atmosphere as input. And then we can output not only the magnetic field, the velocity field, but we can also output the density and the temperature at each of those points. And from those temperature and density, we can then basically compute the emission that we observe. Basically emission and absorption that we would observe at each of those points. which we can then use for like a basic radiative transfer in that sense and match the actual observations that we have in EUV. So that's like planned. Let's see how this then turns out, but it would be an interesting way of actually further constraining density and temperature in the simulation volume within this framework of MHD simulations. So this would be like the long-term goal, more or less.
And I have one last question, which is...
Yeah, sorry.
Otherwise, we can discuss during the coffee break as well.
Yes, very cool. Can you speak very quickly about what the limitations are? I mean, as I understand, it's the boundary conditions. But on the other hand, you don't have a grid per se, right? You just decide which points to sample. Mm-hmm. So this could be very beneficial for simulations like SEP, acceleration and transport, where you have a huge volume, but you decide what to, which points to choose, yeah. And your boundary is actually here closer to Earth. So can you comment on this?
Yeah, that's perfect, and I think it's the perfect method for such applications. So basically, all the resolution that we have in our simulation is only dependent on the actual sampling process that we're having. So when you look at this one here, the way that we perform this random sampling, it's just a uniform distribution in our box. So it's not tied to any grid here. So X, Y, and Z is not integer values, but like smooth values within this simulation box. So right now it's kind of simple in this case. So we just take like a uniform distribution, and we could even like advance this, get it faster, or get better solutions by sampling actually the points that are most interesting. Like in the framework that you were saying, we could, for example, focus on specific regions where we then take like a large number of points, while other regions are very smoothly approximated. And the way that this whole concept here works is that the neural network is extremely good at storing information in terms of in the parameters. So also like what we get in the end is just a couple of megabytes in terms of free parameters that we have tuned, but it incorporates the entire information of this simulation box. So it's basically a huge compression of information, and it can approximate regions that have basically very little information as like a smooth transition, while regions that have the most important parts in them, it can focus on those regions, and it's all depending on the sampling method that we're using. So actually, in that regard, what we are also aiming for is performing this approach for the global sun, and then we could, of course, like most of the quiet sun should be easy to model in that sense, but we can incorporate this sampling procedure to actually focus more on active regions within this entire simulation, focus on them, but incorporate this in a global field solution. So it's also still an ongoing project.
Okay, thank you very much.
Thank you.